Hello. Um, Besides the Heisenberg, Schrödinger, de Broglie, and Dirac formulations of quantum mechanics, Feynman came up with a different reformulation of quantum mechanics, which we call the path integral formulation. And he derived the Schrödinger equation and all of quantum mechanics from the following postulates. First, that the probability for an event is the squared modulus of a complex number called the probability amplitude. This probability amplitude is given by adding together the contributions of all paths in configuration space. The contribution of a path is proportional to e to the power is by h cross, where the action s is equal to integral L dt, that is the time integral of the Lagrangian along the path. So to find the overall probability amplitude for a given process, we add up or integrate the probability amplitude over all possible paths connecting the initial and final states. This path integral formulation of quantum field theory represents the transition amplitude as a weighted sum of all possible histories of the system from the initial to the final state. A Feynman diagram, such as the one shown here, is a graphical representation of a perturbative contribution to the transition amplitude. Now let us take a step back. Now before Feynman, when physicists tried to use the new quantum electrodynamics, that is the theory of the quantized radiation field that we discussed in the previous episode, to calculate in a perturbative manner the energy of an electron in a radiation field, they came up with infinity. Now this was disappointing and also rather embarrassing. In fact, even when they calculated the energy of the free electron, or even the energy of a vacuum, they came up with infinity. Now, Julian Schwinger and Shinichiro Tomonaga in 1948, they showed that when you actually calculate all these integrals in detail for a real physical process, such as an electron interacting with a radiation field, and subtract out the energies of the electron interacting with itself and the energy of the electron interacting with a vacuum, then for the energy of the electron interacting with the radiation field, you get a finite number. Not only do you get a finite number, you get a number which agrees with experiment to a remarkable degree of accuracy. And this happens because these infinities actually cancel out. This process of cancelling out the infinities is known as renormalization, and it earned Schwinger and Tomonaga the 1965 Nobel Prize in Physics, which they shared with Richard Feynman, who introduced Feynman diagrams, which, as we saw, are graphic representations of the interactions between different particles. And these facilitate the calculation of interaction probabilities through what is known as the linked cluster theorem. The linked cluster theorem states that the perturbative contributions to the integrals are determined by all connected Feynman diagrams. So only the connected Feynman diagrams survive, and the disconnected diagrams actually cancel out. Okay. So this accounts for the remarkable relevance of connected Feynman diagrams in quantum field theory. It's because of the fact that they are sufficient to determine the quantum partition function, and the disconnected diagrams cancel out. So instead of laboriously calculating all the integrals like Schwinger and Tomonaga did, and finding out which ones survive, you use the linked cluster theorem to cancel out the disconnected diagrams. So Feynman came up with a set of intuitive rules to construct these diagrams instead of actually calculating the integrals, and each diagram corresponded to an integral. and as we saw from the linked cluster theorem, only the connected diagrams survive, the disconnected ones cancel out. In his book, Surely You're Joking, Mr. Feynman, Feynman describes how he came up with this idea. He was at an academic dead end and not getting any ideas, so he went to a bar and was just watching his friends playing, tossing a frisbee around, and on the frisbee was a medallion or a logo, and as the frisbee rotated, you could see the medallion wobbling, and that led him to think about the electron orbits and so forth, and that actually got him back into the academic mood again, and led to the idea of the Feynman diagrams. In Feynman diagrams, time runs from the bottom of the diagram, which represents the past, to the top, which represents the future. Directed lines represent propagators. So shown here are the propagators for two electrons labeled M and N. Now, because of the CPT theorem, an antiparticle moving forward in time is equivalent to a particle moving backwards in time. So positron propagators are represented by lines which are directed downwards. Each vertex is an interaction, and dashed horizontal lines are interaction lines. So this diagram represents electron-positron pair creation at this vertex, and this diagram represents the annihilation of an electron-positron pair at this vertex. Wiggly lines represent photons, and each graph represents an integral. This diagram represents electron-electron scattering, which can also be represented like this to make it clear that the electromagnetic interaction is mediated by photons, and electron-positron scattering is shown in the diagram here, and this diagram represents electron self-interaction. These are the diagrams for Compton scattering, and remember that in the path integral formalism we have to sum over all the paths. So in this case we have to sum over all the diagrams. Note the energy and momentum conservation. We can now construct the Feynman diagrams for single photon absorption and emission. So on the left here is the energy level diagram. We have the ground state, which can absorb a photon of momentum k and polarization lambda to give us the excited state m, and that is represented by the Feynman diagram here. The ground state absorbs the photon of momentum k and polarization lambda to give the excited state m. Here and in the rest of this episode we will deal only with atoms and molecules, that is particles, and with photons, and so we shall dispense with the use of directional arrows and just use vertical lines instead, with the understanding that the bottom of the diagram represents the past and the top of the diagram represents the future. So we can also represent this Feynman diagram as simply this. Okay, and likewise the in emission, the excited state m emits a photon of momentum k and polarization lambda to give the ground state, which is represented by the Feynman diagram here. The excited state m emits a photon of momentum k and polarization lambda to give us the ground state, or just as this diagram on the right. We can also construct the Feynman diagrams for scattering. The Rayleigh scattering intensity is given by this formula, where lambda is the wavelength of the radiation and theta is the scattering angle. And this strong wavelength dependence, that is the 1 upon lambda to the power 4 wavelength dependence, means that shorter wavelengths, that is blue light, are scattered more strongly than the longer wavelengths or the red light. And this results in the indirect blue light coming from all regions of the sky, which makes the sky appear blue. Okay. At sunrise and sunset, as in this sunset image that I took from Chintakor Island of the western coast of India, the reddening of the sky is because the sunlight must pass through more of the atmosphere, which removes a significant portion of the shorter wavelengths or blue light and the medium wavelengths or green light from the direct path to the observer. And thus the remaining unscattered light is therefore mostly of the longer wavelength, and therefore the sky towards the direction of the sun appears redder. Rayleigh scattering is elastic scattering. The scattered radiation has the same energy and hence the same wavelength as the incident radiation, whereas Raman scattering is inelastic, that is, the scattered radiation has different energy and hence different wavelength from the incident radiation. Thus, in Rayleigh scattering, the absorbed visible light and the emitted visible light have the same wavelength. The upper state of the transition is not an eigenstate of the molecular Hamiltonian in the absence of the radiation field, and such states are called virtual states. In Raman scattering, the emitted visible light has a different wavelength from the incident light. In Stokes-Raman scattering, the emitted radiation is of lower frequency or higher wavelength, longer wavelength than the absorbed radiation, whereas in anti-Stokes-Raman scattering, the excitation takes place from an excited vibrational level of the ground state, and therefore the emitted visible light has a higher frequency or shorter wavelength than the incident light. So here we have again the energy level diagrams for Rayleigh, Stokes-Raman and anti-Stokes-Raman scattering. The common Feynman diagrams for both Rayleigh and Raman scattering are given by the sum of these two diagrams. Remember that in the Feynman path integral formalism, one has to sum over all possible paths. So in this case, we have to sum over all possible diagrams that we can draw. In this case, on the left, it's as if the photon is absorbed first and then emitted, whereas on the diagram on the right, it's as if the photon is emitted first and then absorbed. But note that the state R is a virtual state created due to the interaction with the radiation field, and it has a very short lifetime, and therefore within this lifetime energy conservation can be violated because of the Heisenberg energy time uncertainty principle. But overall, each diagram has to respect energy and momentum conservation. When we have very high intensity radiation, such as is now commonly available from laser sources, then first order perturbation theory and thus Fermi's golden rule is no longer adequate. This makes possible non-linear phenomena such as multiphoton absorption and ionization, second harmonic generation, coherent anti-Stokes-Raman spectroscopy, etc. For example, in two-photon absorption, you have the absorption of a photon of frequency h cross omega to give a virtual state, and then absorption of a second photon to give the excited state. So for two-photon absorption, we have the energy level diagram and the Feynman diagram here, where you have the ground state 0, absorbing a photon of wave vector k and polarization lambda to give the virtual state R, which then absorbs another photon from the same beam to give the final state M. For two-photon absorption from two different beams of energy h cross k and energy h cross k dash, we have this energy level diagram and the Feynman diagrams here. Again, we have to sum over both these diagrams. For spontaneous 2-photon emission, here is the energy level diagram. Again, R is the virtual state, and here are the Feynman diagrams. So we have the initial state M, the virtual state R, and the final state 0 ket. Okay. In second harmonic generation, 2 photons of frequency omega are absorbed and 1 photon of frequency 2 omega is emitted in the forward direction with conservation of photon momentum. Thus we have these Feynman diagrams. Here we have the absorption of the 2 photons and the emission of the 1 photon with twice the frequency. Hyper-Raman scattering is a 3-photon process where the scattered photon has a frequency omega dash, which is approximately twice the incident frequency omega. The mismatch modulus of 2 omega minus omega dash equals a vibrational or rotational frequency of the molecule or lattice. And here are the Feynman diagrams where R and S are virtual states, and again we have absorption of 2 photons of frequency omega and emission of a photon of frequency omega dash, with the difference that the final state is not the same as the initial state because it's a different vibrational or rotational level. Coherent anti-Stokes-Raman spectroscopy, or CARS, is a 4-photon process where 2 intense beams of radiation with frequencies omega 1 and omega 2 are incident upon a gaseous sample. 2 photons of frequency omega 1, the pump mode, are absorbed, and stimulated emission of a photon of frequency omega 2 less than omega 1, that is the Stokes mode, leads to the population of an excited vibrational state, and then to coherent emission at a frequency omega 3, which is equal to 2 omega 1 minus omega 2, the anti-Stokes mode. Here are some typical Feynman diagrams for coherent anti-Stokes-Raman spectroscopy, where R, S, and T are virtual states. So we see that we can construct Feynman diagrams for rather complicated processes, and each of these Feynman diagrams is associated with an integral, and adding up these integrals we get the amplitude for the process.